In this video, we're going to start an example of a titration calculation. So remember, titration, the whole point of it is to use something of known concentration to find something with the unknown concentration. So I have a substance in here with an unknown concentration. I add in a substance of known concentration until a reaction happens. Then I can get volumes, and using volumes and moles and concentrations, I can do stoichiometry to find the concentration of the unknown of the substance I don't know the concentration for already. So we have our burette here, and we have our flask here, and we're trying to figure out the concentration of what's in this flask. So let's go ahead and do some sample problems together. We'll start off with the first question here. How many liters of 3.4 molar HI will be required to reach the equivalence point with 2.1 liters of 2.0 molar? So let's go ahead and solve that problem on our handout. So what we're basically asking in that question is, when we say the equivalence point, it basically means how much is required to neutralize. So we're doing a basic stoichiometry problems with acid bases. Let's first of all write out a reaction between the substances that we see here. We have some hydroiodic acid plus some KOH, and we do a double displacement reaction. This is an acid-base reaction. We get a salt, which is Ki, aqueous, and then H and OH together give you water. H2O, liquid. We need to remember to balance the equation. It looks balanced as is, and we're going to write some information down. So we have a concentration of 3.4 molar here. Here we have a concentration of 2.0 molar. And we have a volume of 2.1 liters. Now, this is not exactly a titration right now. I mean, we already know the concentrations. We basically want to see if we did titrate, let's say the KOH with HI, what volume of HI would be required? So we're trying to figure out the volume of HI required to react completely with KOH in this reaction here, because it says equivalence point, which is when the pH, when the OH and the H plus have completely reacted with each other. So we're looking for the volume. Remember our formula, C is equal to N over V. So in other words, we want to find volume here. And we know volume can be found by doing N over C. So we need N. So what I'm going to do is, step one is write out my equation. Step two, let's find the moles of KOH, because we can do that. We know that the moles is equal to C times V, which is equal to 2.0 moles per liter times the volume, 2.1 liters. You cancel those units out. You do your 2.1 times 2, and you get 4.2 moles. So we have 4.2 moles of KOH. Now, using your mole ratio, since we have a 1 KOH to 1 HI ratio, the moles of KOH is going to be equal to the moles of HI, which is equal to 4.2 moles. So now that we've found the 4.2 moles, the N value over here, we can go ahead and find the volume. So volume is equal to N over C, which is going to be 4.2 moles over 3.4 moles per liter. Cancel out moles, you're left with liters. So 4.2 divided by 3.4 gives you about 1.235294118 liters. And for the sig figs, it looks like we have 2 sig figs. So it's approximately 1.2 liters required. So you'd have your therefore statement. So therefore, 1.2 liters of 3.4 molar HI are required to react with 2.0 molar with, I should say, 2.1 liters of 2.0 molar potassium hydroxide to equivalence point, basically to that neutralization point. Now, you can probably guess if this is a perfect neutralization reaction with no excess, no limiting, stuff like that, if they reacted perfectly with each other as we calculated here we have a strong acid and a strong base. So at equivalence point, the pH should be 7, assuming that you reacted them perfectly with each other. If I put exactly 2.1 liters of this 3.4 molar hydroiodic acid with this strong base KOH here, I should be at pH of 7 once equivalence point has been reached. So that was our first example. We were using known concentration and known volume to predict how much of this acid volume-wise should completely react with this known stuff over here. So we didn't have any unknown concentrations in this case, but in many titrations that you do, you're doing that to find an unknown concentration. Think of this kind of like a warm-up with stoichiometry, and understand that it really, even these titration problems will just be stoichiometry just to find concentration of something or volume of something. So in the next video, we're going to take a look at the next example, but make sure you understand this one over here completely before you move on to the next example.